Okay, so today we are going to look at timing diagrams. So basically in timing diagrams we are going to see that for a particular instruction how many clock cycles are going to be consumed. Okay, so already we have learned that we are having a 16 bit address bus, 16 line address bus which is having 16 bits. So and also we know that 8 bit data bus and 8 bits of address bus are multiplexed, that is 8 bits of 8 lines for data bus and address bus are common and these 8 lines are separate. So this is going to be completely the address bus. This is going to behave as address bus or data bus depending on the status of this address latch enable. This ALE stands for address latch enable. If this ALE is 1, the value for ALE is 1, this is going to behave as an address bus, and when this ALE is 0, this is going to behave as a data bus. This signal is read bar. If read bar is 0, the processor is going to read something from the memory. If read bar is 1, this line, if this line is high, therefore no reading procedure will take place. Now we have taken a simple instruction, basic instruction MVIB03H. MVIB03H is going, this instruction is going to do is, this is going to load this data 03 in hexadecimal in B register, Now see, all the instructions are going to be already going to be loaded in the memory. Suppose the location of this instruction, starting address of this instruction is 2000. So MVIB is a 1 byte instruction. Address for this data 03 is going to be 2001. Now just we are going to look from the starting. Suppose here time is 0. Here we are setting the clock. Now what is going to happen first? First we are going to load the address of first instruction. Address of first instruction is 2000. Now see, we are dividing into two blocks because the address is in hexadecimal. Each is having 4 bits and we can only allow 8 bits. So we are dividing this in two. Higher address goes in higher address lines and this lower bits of the address goes in lower address lines. So here we are going to put 20, here we are going to put 00. Now we have enabled the ALE, address latch enable. What happens when we enable the ALE? When ALE is 1, this bus is going to behave as an address bus. So now it is behaving as an address bus and it is carrying address 2000. Now what it is going to do is, it is going to take the processor to the memory location 2000. Now when it reaches there, we get the opcode. What is the opcode? Suppose the opcode is EF. Here we know the opcode is MVIB. So MVIB gets loaded in this data bus. Now this bus is behaving as data bus. Since ALE is 0, ALE is low, so now this bus behaves as data bus. Now we just make read bar 0. When we make read bar 0, see this is having a bar. So when it is 0, that means this line is going to work. What does this mean? We are going to read this instruction. The processor has read this instruction. Now see here, what here is, this is the decoding cycle. This is the decoding cycle. Decoding of the instruction takes place in 1 clock cycle. 1 clock cycle is required for decoding of the instruction. The processor interprets what instruction has been given. This data bus, this address bus and data bus, this behaves unspecified. This is high impedance. Okay, this is high impedance. See, we do not require this bus in this clock cycle, that is why we have made this high impedance. Now what happens when this location is done, when we are done with this memory location 2000, we move on to next location which is 2001. So now again what is going to be loaded here? Here we are going to have 20 and in this we are going to have 01. Again we make ALE as 1. So that this bus acts as an address bus. When this acts as an address bus, we reach the address 2001. Now see what is stored in 2001, we are having the data 03H. So we get here 03H. Again we have made read bar equal to 0 so that we are able to read this data. Now what happens is, we have got the instruction, the microprocessor decoded it, and successfully we know that what has to be done. We have to load the next coming bit, next data in register B. When the microprocessor knows what has to be done, it goes to next position, fetches the data and successfully loads it into B. Now see, these 4 clock cycles, 1, 2, 3, 4, these 4 clock cycles are required for opcode fetch. Opcode fetch. See, MVIB was the opcode. To fetch these opcode, we required 4 clock cycles, 4 T states, 4 T states. And these 3 clock cycles, last 3 clock cycles were required for memory read. Memory read. So, 3 T states were required for memory read. So, this instruction MVIB03H requires a total number of 7 T states, in which 4 T states are required for 1 machine cycle of opcode fetch and 3 states were required for 1 machine cycle of memory read. Okay. Okay, now we are going to see the timing diagram for another instruction. The instruction is MOV B, E. This is a simple instruction of register addressing mode. What happens through this instruction is, whatever the contents of E, suppose E is holding, suppose E has 16 stored. So, what happens after this instruction is, the contents of E are going to be moved to B. After execution of this instruction, contents of B are going to be 16. So, let us see what happens. Suppose starting location for this instruction was 2000 in hexadecimal, of course. So, what we are going to do, see, this instruction does not involve any memory read, any memory write, because both the data, the destination and the source all are lying in the microprocessor itself. Memory is not involved. So, we are only going to need one machine cycle for opcode fetch, and also in the same machine cycle we are going to execute the instruction. Now, what we are going to do, same thing we are going to do, we are going to put the address on the address bus. I am going to put 20 here and 00 here. We always put higher bits of the address in the higher address bus and lower bits in the lower address bus. When we have put 2000, we make ALE1 address latch enable, so that this bus behaves as address bus. Now, this is behaving as address bus, the address is 2000. When sorry, when we reach there, we get the opcode. What is the opcode? MOV B, E. See, now since ALE is not 1, since ALE is low, ALE is 0, this bus is going to behave as the data bus, and also we are going to make read bar as 0. When this line is low, when this read bar is 0, we are going to read this data, we are going to fetch this data from the memory. So, now we have got the data. Now, in this cycle, in the 4th T state, what is going to be happen? This the contents of this address bus are undefined, unspecified, and this bus, this multiplexed bus, this is going to be high impedance. See, we are making this bus as high impedance because we do not want the data of this bus to change. We do not want the data of this data bus to change. That is going to cause errors. I just want that MOV B, E should remain in the data bus, so that whenever I need, I can access this. In this cycle, what is going to happen? We are going to have here decoding and execution. Since no arithmetic logical operation or any memory access cycle is involved, we are going to perform decoding and execution in one same T cycle. So, this instruction is going to take a total of, okay, we only needed opcode fetch, only opcode fetch was needed, and opcode fetch needed 4 T states. 4 T states. So, this instruction took 4 T states. See, machine cycle is different and clock cycle is different. What we are counting here are T states are the clock cycles. Machine cycle is this opcode fetch, this is one machine cycle, memory read is one machine cycle, memory write is one machine cycle. So, one machine cycle may be of variable clock cycles, like here one machine cycle of opcode fetch is of 4 T states. Similarly, Suppose we have some other operation. Let us assume we have gotten instruction add b. Add b. First, just look what this instruction is going to do. What this instruction does is, suppose the contents of accumulator were 0, 1 and contents of register B were 0, 5. Now, after I execute this instruction, what is going to happen? Contents of B are going to remain unchanged. We are going to have 0, 5 here only. And what happens to A register? Contents of B are added to A and the final value is written in the accumulator itself. So, in A we are going to have 06H. So, here we are involving an arithmetic operation, but again see, since we are not required to access the memory, the contents of B, contents of A and also the ALU unit lies in the microprocessor itself. So, we are not going to require 2 machine cycles. In 1 machine cycle only we are going to do all this. Okay, fine. So, the starting address for the instruction is 2000. So, again in the address bus we are going to put 20 and 00 here. We are going to enable the address latch enable, ALE is going to be 1, so that this bus behaves as address bus. When this bus behaves as address bus, we reach the address 2000 and fetch the instruction add B. We are going to get add B here. When we have made ALE 0, that is we are just using this as data bus. We read this instruction. Now add B is going to be executed. In this same cycle, the instruction is going to be decoded and executed. So the address bus is going to be unspecified and this bus, this multiplex bus is going to be high impedance. Other ALE is going to be 0, read bar is going to be 1, that's okay. So in this time, in this clock cycle only, we are going to add these values and the final value is going to be written in the accumulator. Similarly, for any given instruction, any opcode fetch, see any opcode fetch instruction, any opcode fetch cycle is going to be 4 T states only. It is going to take 4 T states only. First T state, you are going to put the address, you are going to make ALE 1. And then in second T state and third T state, it takes 2 T cycles to read from memory. If you are going to involve memory anytime, you are going to write in the memory, read in the memory, you are going to require 2 clock cycles, 2 T states. So, to read the data, you are going to require 2 T states. Then for decoding, you require 1 T state for decoding. So, generally in all opcode fetch you are going to require 4 T states. For opcode fetch of any instruction 4 T states are required. Generally for memory read you are going to require 3 T states. We just had a look in the first example how you are going to read the data from the memory. Okay. And for memory write also generally 3 T states are required. Okay, although there are some other timing diagrams. Okay, let us have a look at another timing diagram. Okay, now let us have a look at instruction MOV M, B. Okay, firstly what happens in this instruction is contents of register B, suppose B is holding 16H. M means memory location, address of the memory is indicated by HL pair. Suppose HL pair contains some value 2050H. So what happens after execution of this instruction is contents of register B are going to be written in the memory at location 2050H. That is, suppose this is the location, this is the memory. At some arbitrary location this instruction was saved. This instruction was saved at suppose 3000. So we start our cycle from 3000, we fetch this instruction MOV M, B. After decoding of the instruction we are going to go at the, suppose this is location 2050H. So you are going to go at this location. Initially if it was having some value 25, suppose it was having initially 25, this value is going to be overwritten with contents of B, that is it is going to be overwritten with 16. Okay, now let us look how this is going to work. Okay, firstly we are going to, this is the address bus. So in this address bus we are going to put the address of starting address of this location. I am going to put 30 here 0 0 in the lower address bus. For this to behave as an address bus, we are going to make ALE 1. Okay, ALE is going to be 1. This is address latch enable. Fine, in one cycle. Now what happens in the next cycle? Okay, fine. What happens in the next cycle? As soon as you make this ALE 0, that is address latch is not enabled, this does not behave at address bus and behaves as data bus. What data is going to come in this data bus? See, data stored at location 3000 is MOV M, B. So you are going to get MOV M, B loaded in the data bus. To read this instruction, you are going to make, you will have to make read bar as 0. This is read bar. So you make read bar 0. As soon as you make read bar 0, you are going to get MOV M, B in this data bus. Now next cycle, this cycle is going to be decoding. When decoding happens, this bus is unspecified. That is, contents of this bus are unspecified, and this multiplex bus is made high impedance, so that contents of this data bus do not change. Okay, so now we have already got MOV M, B in the processor. Now the processor knows that contents of B have to be written in the memory, the location pointed by HL pair. Now the processor reaches the HL pair and sees what is stored. So see, what was stored in HL pair? HL pair contains 2050. So in the next cycle, we are going to have 20 and 50, 20 and 50 stored in the address bus. Again, for this to behave as address bus, you are going to have to make ALE as 1. ALE as 1. Okay, so we have given the address now 2050. Now see, okay. Now see, what we want is, we want to write the data. Since you have given the address, you have given ALE as 1, so you have reached the address 2050. Now what do you want to do at the address 2050? We want to write this data, we want to write 16 there. So what do? As soon as you make ALE as 0, we do not enable this latch, and what happens? This bus is going to need data. Where does it take data from? What data does it take? It takes 16. 16 is the data that you have to write, and to write this data, what do? We use another signal, which is WR, write bar. We are going to make write bar as 0 for this duration. As soon as you make write bar 0, this data is going to be written in the memory location 2050, which was pointed by HL pair. So this is a timing diagram for memory write. Just see here. See these 4 cycles, 4 T states. These 4 T states, first 4 T states are used for opcode fetch. Opcode fetch, that is to fetch MOV M, B. Opcode fetch is taking 4 T states, and the next 3 T states, these are used for memory write. Memory write is using 3 T states. Okay.